Hello, my name is Peter Kramer, and this is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. Semantic memory contains our general knowledge about the world. Most theoretical perspectives see semantic memory as some structure, such as a network or a high-dimensional vector space, that carries representations of concepts and the relationship between them. Thereby, the degree to which a given pair of concepts, like clothes and animals, is related can be operationalized as a variable we call semantic relatedness. Semantic relatedness depends on the distance of two concepts in the representational space, be it the edge length and the number of nodes between concepts, or a Euclidean-like distance in a vector space. Importantly, as cognitive scientists, we often assume that cognitive processes operate on these structures. For instance, memory retrieval is typically understood as spreading activation in a semantic network. This has led to the question how we can disentangle memory structures and memory retrieval processes. In this talk, we want to go even further and focus on the decision processes, which depend on both memory structure and memory retrieval, and ultimately guide behavior. We focus on the semantic relatedness decision task. This is a fairly simple paradigm where participants are confronted with two concepts and they need to decide whether they think the concepts are related or not. Traditionally, choices and response times in this task have been used to make inferences about the structure and processes of semantic memory. When participants perform this task, empirically we see that these response times describe an inverted U-shape as a function of semantic distance. Response times are low when there are few nodes between the concepts and they increase up to a certain level. And when the distance is large, response times are low again. Now, the usual interpretation of this finding is that spreading activation just takes more time to spread through the network when the distance is larger. While this view could explain the left and the middle part of the curve, it neglects what's going on the right-hand side. Also, it neglects the decision conflict that needs to be resolved, especially in cases where concepts are borderline related. From a perspective of decision making, this finding looks much more like the difficulty effect, where easy decisions can be made relatively fast and hard decisions take longer. Overall, choices and response times in this task likely depend on both memory and decision processes. And this led us to the question how we can model the respective memory and decision aspects that give rise to the behavior in this task. We resorted to the sequential sampling framework. Sequential sampling models describe a decision as noisy accumulation of evidence over time until a decision threshold is reached. A very simple sequential sampling model is the race model. Here, two accumulators race to a decision threshold, and the first one which hits the threshold specifies the choice and response time of this decision. The orange accumulator causes a related response. It depends on the semantic relatedness between two concepts in a trial. Analogously to signal detection theory, the evidence for responding related is compared to a criterion value or a reference value which has its own accumulator. When there is relatively more evidence that items are related, an agent will more likely judge them as related, and vice versa. The race model can be equipped with an additional lateral inhibition parameter, as has been done in the context of the leaky competing accumulator model. This inhibition specifies the response conflict between options as the momentary evidence of each accumulator inhibits the other accumulator. When the rate of the orange accumulator is much larger than the rate of the blue accumulator, the accumulators diverge early and the choice can be made relatively quickly. When the difference between the accumulators is small, the traces diverge later and the response times take longer. Finally, we also consider a 4-parameter drift diffusion model where relative evidence is accumulated as a function of difference between the relatedness of the words and the reference value. We wanted to know if and how these models can account for the inverted U-shape of response times. To do this, we simulated data for plausible parameter values and tested if the simulated data would reproduce the inverted U-shape. We operationalized semantic relatedness as values between 0.09 and 0.6. These values come from word-to-vec cosine similarity values of a representative set of word pairs, published by Bruni and colleagues. We chose reference values which covered parts of this range. All other parameters are inspired by parameter recovery study by Miletic and colleagues. In this graph, we plotted response times of simulated data against semantic relatedness. Pooling all simulated data, we observe that the LCA and the DDM, but not the race model, can predict the inverted U-shape. Looking a bit more into the effects of specific parameters, we observe that the U-shape depends on the reference value, the threshold, and the lateral inhibition. Further, the DDM was able to reproduce the inverted U-shape. This suggests that the lateral inhibition of the LCA and the relative accumulation dynamics of the DDM are chiefly responsible for the model's ability to account for the inverted U-shaped relationship. Next, we wanted to know if the models can also account for the relatedness effect, a phenomenon that participants make related responses faster than unrelated responses. This has been reported quite consistently across the literature, but yet there is no formal account of how this effect comes apart. Looking at the pooled simulations, we see that the race model and the LCA produce a relatedness effect. This may be due to the higher accumulation rates for related accumulators, which cause slower unrelated responses. The DDM, on the other hand, produces the relatedness effect only when the starting point bias favors the related response. We took a closer look on how the relatedness effect depends on the difference between semantic relatedness and reference value. We plotted the relatedness effect as Cohen's D against this difference. For the race model and the LCA, we observe a positive relationship. This relation scales with threshold and lateral inhibition. The DDM, on the other hand, produced a relatedness effect only as a starting point bias, which you can see down here. Please note that this only holds for the 4-parameter DDM, which we considered here. If you would include a drift rate variability, a DDM could also produce the positive relation that the race model and the LCA predict. We found the predictions of the race and the LCA models particularly interesting. They not only predict the relatedness effect gets larger with increasing difference, they also predict that the relatedness effect can reverse, producing an inverted relatedness effect, so that unrelated responses are faster than related responses. This is if semantic relatedness is smaller than the reference value. Thus, when the relatedness tends to be high, we'd expect a classic relatedness effect. When the relatedness is low, the effect flips. Statistically, you would expect an interaction effect of relatedness and choice outcome on the response times. We tested these predictions on an openly available dataset by Kumar and colleagues, who asked 40 M-Turkers to do the semantic relatedness decision task. In each trial, participants saw 2 words and decided if they considered them as related or not. For every trial, we computed the cosine similarity of the word pairs as a proxy for semantic relatedness. As you see, the empirical data yielded a similar pattern as predicted by the race and the LCA models. We applied a hierarchical linear regression model to test if this interaction effect was credible, and the 90% highest density intervals of the posterior mu of the interaction effect excluded 0. Thus, we observed empirical evidence for the predictions made by our sequential sampling models. To sum up, our main point is that memory tasks are also decision tasks. When we model behavioral data, it is likely that both memory and decision processes contribute to the behavioral outcomes. By focusing on a relatively simple task, we showed that the sequential sampling models can be adapted to investigate the dynamics of memory-based decisions. Everything I've presented here can also be found as a preprint on SciArchive or in this year's CogSci proceedings. So, where do we go from here? At the moment, we are testing further predictions of the LCA on new data. We ask whether base rate-like effects, which we know from episodic memory research, can cause shifts in the reference value. Also, we ask whether these semantic relatedness decisions depend on speed-accuracy trade-offs. In the future, I'm interested in how far we can use modeling to tease apart memory structure, memory retrieval, and decision processes, and if this may also help us to identify neural signatures of these process components. So if you would like to chat about any of these topics, please feel free to contact me via mail, Twitter, or during the Q&A session. And with this, I would like to thank my collaborators, Dirk Wolf and Sebastian Gluth, and of course you for your attention.